Okay.
He goes like
I'm creating basically a solutions manual for the homework.
You know there is one, right?
Well, the author gives hints and stuff like that in the
No,
back.
there's like a legitimate, I have one. Like it's a solutions page.
With proofs written out?
Yeah.
Are they good?
Pretty good.
Because we wasted way too much time in class
I can show you it if you want.
going over those. Yeah, so do you have it as a PDF?
No.
Oh, you just have a physical one?
No, it's a website.
Oh, it's a website?
So you're saying you're going to go through every homework problem, solve it. And
Yeah, I've been solving
Oh,
every
you can
single
just use my
homework
homework.
problem. And then, well, that's not good enough, because I need it typed out a good solution. So that they have an example as their, they need to do exactly what you guys are doing right now. They need to get used to informal proofs, what you can and can't do.
Mm-hmm.
And I think one of the best ways to do that is to just have a ton of examples. So let's see.
I don't know if you're fashion state.
That's what I was doing.
It's like,
That's pointing.
Oh, you have
have
to
you
take
ever
it for
seen
the
the
load?
Heisman Awards?
Well, I'll have to look at that. 'Cause yeah, if that's good solutions. That would save me
Oh,
some
yeah,
more.
it is dangerous.
All right.
Actually sexy.
So we're starting chapter 7 today. Chapter 7, transition from formal to informal proofs. So from here on out, when we say the word or use the phrase formal proof, we're going to be talking about I probably won't love the way they do their proofs, but using it for, will you text me the URL for that website? Thanks. But for just even checking my own work, and then for the ones that's just like writing out a list of numbers, that should be good. Anyways, so from here on out, when we use the word formal proof, we're referring to how proofs were done at the start of the book, where you do every line, you write exactly the rule of logic or the axiom that you're using, listing out your premises, etc. Now we're shifting over to informal proofs, which we've already been, or at least I've already been doing quite a bit of, and doing in a fairly lazy way. And the number one, the minimum for when you're doing an informal proof is someone should be able to take your informal proof and construct a formal proof from it. It should have the crux of the proof in there, the trick that it took, the realization that you needed, the thing that makes it obvious to someone who's at your same level, oh yeah, that's what you need to do to prove that. So it needs to capture the essence of that thing, at the very minimum. And however you need to explain more is however you need to explain more. There shouldn't be any dispute going from one line of your proof to another line of your proof. So Jacob writes a proof, and Peter can't get from line 1 to line 2, Jacob messed up. That's a good strategy for when you're writing proofs for the first time is think about what one of your contemporary students in here would understand. Would they be able to go from point A to point B? If not, fill in more detail. If so, you've covered what you needed to. Outside of that is just explain what you think helps give more insight, helps the student or whoever's reading it understand your proof. But again, there's no hard, fast rules for how exactly these things should be, which is why we have the formal proofs to fall back on, where everything has rules, very specific rules, and you have to follow the rules, no exceptions. So what the author does, so 7.1 is just a brief discussion like that. 7.2, he gives us these axioms. I think he just calls them numeric axioms.
So now are we actually building?
So you remember in calculus we said the real numbers is a set that satisfies these axioms.
Yeah.
That was these axioms plus one more. And then
So now
you got
we're
real
building.
numbers.
We're building mathematics then, or
Yeah, we're going to be doing some very what we're doing today is going to be very similar to what we did in the preliminary stuff for calculus. We're going to do some identical stuff. This author chooses to capture the information in these axioms different than our textbook did, but they're logically equivalent. And so we'll be proving some of the exact same stuff. But as these axioms are listed, either the real numbers with multiplication and addition satisfy it, or the rationals with multiplication and addition satisfy it. Does anyone not understand what I mean when I say real numbers or rational numbers?
Irrational or rational?
Rational?
Aren't the rational numbers a subset of the real numbers?
Yes. The rationals are a subset of the reals. The irrationals are a subset of the reals. The irrationals are all the real numbers that aren't rational. Am I losing anyone in that?
Yeah,
Do you know what a rational number is?
yes. It's
What's-
just like integers.
An integer is a rational, but a rational isn't necessarily an integer. So, the rationals are any number I can express as a fraction of two integers. So, 1/2 is a rational. It is not an integer. However, 3 is an integer. Is 3 a rational?
Yes.
Yes, because that's the same thing as 3/1. There we go. So that's what a rational number is.
Irrational is just jump by one, but they go negative.
It doesn't really matter what the irrationals are, but so you know what a rational is. It's all the numbers that can be expressed as fractions. And then when I say a real number, chances are, in your mind, that's just any number.
Rather than a complex.
So for example, square root of 2. That's a number. It can't be expressed as a fraction. There's no fraction you can find that equals the square root of 2. But you know that's a number. So when I say real number, you probably, anything you would know to be a number is a real number. For those of you that know what complex numbers are, then you obviously know the difference between real numbers and complex numbers. But for those of you that don't know complex numbers, chances are anything you think of as a number is a real number.
Complex numbers are part of the real numbers.
No,
Okay, I was just gonna say.
no, no, no. A real number is a complex number, not vice versa.
Right.
Okay. So, you can think about these numbers as being real numbers, or you can think about them as being rational numbers for everything that we do here, and it works.
That's our domain
And
for
then-
all those axioms.
Yeah.
I wouldn't
So we'll just, let's just put that up. We'll just think about our domain as a set of all real numbers. That's a shorthand for the set of all real numbers. So that's the domain that we're talking about. So everything in here is just real numbers. And we're talking about the addition that you know and love, and we're talking about the multiplication that you know and love. So we're just talking about real numbers, addition, multiplication. Straightforward arithmetic. Make sense?
Yeah.
Okay, let's really quick go over each one of these axioms and make sure that we understand it. For any two real numbers, it doesn't matter what order you add them, and it doesn't matter what order you multiply them. Or in other words, addition and multiplication are
Commutative.
commutative.
Got him. There you go.
Alright, let's look at the next one, axiom 2. For any three real numbers you have, you can do the first plus the second plus the third, or the first plus the second plus the third, and you get the same thing. Similarly with multiplication. Everyone understand what this is saying?
Yeah.
In other words, it's saying, maybe write an example real quick. It's saying if I do, well, it starts with parentheses here, 1 plus 2 plus 3. How do I solve this? I do the addition here. I get 3 plus 3, I get 6. I get the same answer as if I were to do 1 plus 2 plus 3. 2 plus 3 we know is 5, so 1 plus 5, 6. That's what it's saying. Similarly, if I replace those plus signs with multiplication, the number I get over here and the number I get over here is going to be the same number. That's what it's saying.
And it's not possible to prove that with the other axioms?
Not from these axioms, no.
Okay.
Nope.
Where?
It's possible to prove it all with any axioms? Like,
Remember, it's anything you want is provable, just depends on where you're willing to start.
right.
Right.
So yeah, I could come up with some different system and then prove this from that system.
Right.
Sure. But
Just wondering because in our discrete math class, we would look at sets of numbers and we would look at properties and prove that they are transitive and associative and stuff like
on relations.
that. Right.
Yeah, we would prove that with relations, and I don't know if I did with you guys or the previous class, we got into some group stuff. So, we also did that in this class. We talked a little bit about group theory.
Mhm.
If you remember with group theory, the operation was associative, but it was not commutative.
Right.
So not any system of numbers and operations has these properties. It just so happens that the plus and multiplication on the real numbers has these things. Right? Okay. So we all good with these two axioms? It's important that we understand these. So if anything feels weird, let's get it out of the way now. Because these never go away. These are here to stay forever. So we're good with these two? Alright. Next one. Yeah, this is how you distribute multiplication over addition. If I have x times y plus z, that's the same thing as x times y plus x times z. What does that mean? That means if I have 3 times 2 plus 5, that's the same thing as 3 times 2 plus 3 times 5. Let's look at it real quick. 2 plus 5 is 7, 3 times 7 is 21. 3 times 2 is 6, 3 times 5 is 15, 6 plus 15, 21. Whoa, it worked.
Wow.
Wasn't expecting that. So we give it distribution. All right, next one. The next one is saying that we have a right-hand identity element for both operations. That's one way of saying it. So we're saying that there are two real numbers. We're going to call them 0 and 1. We can call them whatever we want. The whole world calls them 0 and 1, so we're going to follow that convention. But the fourth axiom says there are two real numbers such that, call them 0 and 1, such that any number plus 0 always gives you back that number, and any number times 1 always gives you back that number. So adding 0 or multiplying 1, don't change it. Good?
Okay.
We all know how to add 0? We'll see.
It's really hard.
You're going to get tested on it. You think it's easy.
You think
We'll see.
it kind of messed me up the first time we did sweet math.
What the heck?
There'll be proofs where you'll need to add a 0 to
You can write 0 a lot of ways.
A lot of ways.
All right. Next one.
I don't even get that.
You didn't get that?
What I'm saying is not just not in calculus.
In
no.
calculus.
We'll write some zeros.
Okay.
All right. I'll write one for you right now. You're welcome.
Wow.
All right. Next axiom. Next axiom says, for any number, there exists some other number such that their sum is 0.
I like that one.
Another way to say it is every real number has a multiplicative inverse.
Yeah.
For
And
every
that-
number
that's-
you pick, there exists some other number such that their sum gives you the additive identity. Did I say multiplicative before?
Yeah,
Yes.
sorry, additive inverse.
Scratch that. For every number, there's an additive inverse. For every number, there exists some other number such that their sum gives you the additive identity.
So
the
you're
real-
introducing negatives.
Basically.
Okay.
Now, this doesn't say that there's one and only one. We're going to prove that later. I know, for example, if x is 3, there's one and only one number, namely negative 3, such that their sum is 0. So this isn't telling us that there's one and only one. We'll get to that later and prove that that's the case.
Hey!
This is telling us that there's at least one.
What's that in calculus? One and only one. I remember that proof.
Yeah, very basic stuff that you do. Okay, so everyone good with this axiom? Any questions here? Anything weird? All right. Next one. Next one's pretty similar. Oh no, it's not.
Isn't there a role for
Okay.
a multiplicative inverse on the real numbers?
We're not going to get to that one today. Maybe we can just do it anyways.
Is that an axiom or is it a proof?
He's not getting into it in chapter 7, and you can get some intuition for why real quick. So when you get multiplicative inverses, then obviously you're working towards division. And what's the big scary thing with division?
You can't divide by 0.
You can't divide by 0. What do we say? Division by 0 is
Undefined.
undefined, and the next chapter is definitions. So he's intentionally putting off working with multiplicative inverses for now.
But is it actually an axiom?
Well, this one gives us what we want.
Okay.
So this is the axiom that helps us get our multiplicative identity, or our multiplicative inverse that we want, but we're not going to be touching on that today, specifically because we don't want to talk about division by zero until we go over a definition, what definitions are. And then we can talk about why any number divided by zero is undefined. You can't define it. It doesn't make sense to try and define it. Anyways, so let's make sure that this one makes sense. For any two real numbers, x and y, as long as y isn't 0, then there exists a number z such that y times z equals x. So that one might seem kind of weird, so let's do some examples real quick. Give me any two real numbers you want, x and y.
1 and 2.
1 and 2. So I'm saying for any two real numbers you pick, I can always find a third number z such that this equation is true. In this case, it's 1/2.
Right. It's basically multiplicative inverse.
Kind of. Multiplicative inverse when x is 1.
Yeah.
Then z is the multiplicative inverse of y.
Is this like the same definition that discrete math uses for divides?
We don't have a definition for divide yet. This is an axiom that numbers satisfy. So you'll notice as we're going over here, we're going to eventually get to a definition of a negative number. We're going to eventually get to a definition of subtraction. So we'll develop definitions down the road, but we are not talking about definitions right now.
So why are we
Well, we're in the
developing
domain.
so many definitions and then not talking about definitions?
Why are we developing?
I'm saying, well, why do we have so many definitions? We're talking
We're-
about definition 1 and definition 2, and yet we're not talking about definitions.
No, right now we might.
Oh, you're saying because chapter 8 is definitions.
Yeah.
Why aren't we covering definitions before we cover this? It's going to be examples, rigor, examples. So examples of definitions, rigorously cover definitions, then more examples that come up in hard cases.
Okay.
Fairly common strategy.
Just like it off.
Okay. So are we all good with what this one's saying?
Yeah.
You sure?
Yeah.
All right. The next one. For any two real numbers, if x is less than y, then it is not the case that y is less than x. Make sense?
Yes.
Okay. I think that one's pretty straightforward. Next one. For any three numbers, x, y, and z, if x is less than y and y is less than z, then x is less than z. Or in other words, the less than relation is
Transitive.
transitive.
We've already proved this one, though. No, this set of axioms, what we did earlier. With a different set of
We might have proved some relation is transitive.
We didn't prove transitivity in itself.
No,
but
we've used this
Right.
before.
Yeah.
We didn't what?
we didn't prove that axiom basically, but we used it.
No, you can't prove an axiom.
Right. That's the point.
Otherwise, it's not an axiom.
Well, okay. You can prove the axiom with a different set of axioms, right?
What do you-
What I'm saying
If
is.
you prove it, it's not an axiom.
Right. Okay. Terminology right now. We can prove axiom A with a different set of axioms.
Yes,
And
I can
again,
choose
earlier.
different axioms and make these things theorems if I wanted. That's possible. But these are good enough. Okay, so we did that, we did that. This one. If x, for any two numbers x and y, if x is not equal to y, then either x is less than y or y is less than x. And we'll see later that it can't be both, but that's all the information we need for the axiom. This one good?
Yes.
Nothing weird? Next one, for any three real numbers, x, y, and z, if y is less than z, then y plus x is less than z plus x. In other words, if I have this less than inequality, I can add the same number to both sides, and the inequality is still true. Make sense? And then this one basically says if I have an inequality and I multiply both sides by a positive number, then it's still true. So let's read it how it says it. For any three real numbers x, y, z, if x is greater than 0, or if it's positive, and y is less than z, then y times x is less than z times x.
You need to switch your greater than sign.
Where?
It-
For what?
Oh,
Y?
sorry, never mind. I screwed
Right?
up.
here's my inequality,
I have a
and I
question.
multiply both sides by a positive number, the inequality is still true, exactly as it was.
Last week you said that on an equality, or with an equal sign, it's just a rule of logic that you can do that. You can add the same number.
With identity. It only works with identity. It only
Well-
works with the equals relation.
Are you
Identity.
dealing with identity right now?
No, that's less than.
Well, I'm talking about up there we're dealing with identity.
Up here?
In any axiom. Yeah, that's identity right there.
Yeah, that's talking about identity.
Okay, so my question is, can you multiply just like you could have added?
Yes, for any operation, it does not matter. If I know that x is equal to y, then I know that x star, circle, whatever, any operation, plus times divide, x operation z is equal to y operation z. If I know this, I know this.
Right.
What's the proof? This is always true. Right?
Right.
A definition of identity, that's what we said. This is based on the empty set of premises, and then substitute in a y for an x.
Boom.
So yeah, that's a rule of logic. So that's not going to be an axiom here, because that's not dependent on the field of math that we're developing here. That's true for all logic, so we don't need to take the time to specify this. You can always do that. Doesn't matter what field of math you're talking about. So for our particular field of math, it also happens to be true, and we don't need to specify it. The same way that we don't need to specify what and is or what or is. Logic does that. Okay,
1 is not 0.
we finished here? And then the last one, yeah, the non-trivial
Why is that
axiom.
necessary as an axiom?
1 is not 0,
Yeah, like,
so that we don't just have a one element set.
We now are dealing with 2 numbers.
So we have at least 2 numbers for sure. Think about just a set 0.
okay.
So that every time we're talking about anything, we're talking about 0.
Uh-huh.
Everything's satisfied.
Right, but if the real numbers is the set of numbers that satisfies these axioms, and there's a lot of other numbers.
Well, and the rationals. Yeah, and we can show that that's what you need. So for example, once you have 0 and 1, and those aren't the same, now I need to know what 0 plus 1 is. Oh, that's 1. Oh, so 1 something in there. Well, now I need to know what 1 plus 1 is. Oh, that's 2. Okay, now I need to know what 2 plus 1 is. Oh, well, that's 3. So once you give me 1 and 0, you can see how I could easily get all the natural numbers, but the inverse is how I can get the integers, and then with this one, how I can start getting the rationals.
Where do you get the reals?
Well, same thing, but we don't necessarily have the reals right now. The rationals satisfy this, the reals satisfy this.
But you get
I'm not guaranteed the reals from these axioms.
so you get the reals when you get the
When I add the completeness axioms, I have to be talking about the reals.
Is that axiom 13?
Well, for how I even labeled these different than the author. The author has 15 axioms in there.
why?
Because I did stuff like this.
And
Oh. Okay.
Because I didn't want to write that stupid for all x, y over and over again. Okay. So we understand the axioms. We're good. Now my theorems, when I switched to writing my theorems, I dropped all the for all stuff over and over again. So when I'm saying x plus y, y plus x equal to y implies x equals 0, that should really be for all y for all x, then this is true.
Right.
And as we develop math, we typically drop off the quantifiers unless for some reason it's needed.
Right.
So, for example, no quantifiers, okay, here we have a quantifier. Oh, we have a special quantifier.
There exists exclamation mark.
There exists, and I put an explanation point after it. Anyone know what that means?
I wanna say a single
It doesn't
thing,
seem
but
like you're talking about factorial here, so.
No, you can't do a factorial.
One and
there
only one.
exists one and only.
One and only one.
Yeah.
So there exists, the way we've been using it before is there's at least one. This means there's one and only one. So we're going to eventually prove that there's one and only one number y, such that x plus y equals 0.
There exists.
And that's going to be negative x. Huh?
I just make it fun.
Did I say it weird?
No. Just the terminology of reading it out loud.
Okay. So, let's start going through some of these theorems. And we'll do informal proofs to start with, and then I'll get lazier as we go on, and they won't even be that. They'll just be scratches up there that make you feel like you could reproduce a proof, even though you really couldn't.
That's how I know this.
That's exactly accurate. That is so true.
Yeah, that is a point I probably make. You're going to watch me do proofs up here, and you're going to think that makes perfect sense, that makes perfect sense, I could easily have done that, I could easily have done that. And then if you were to try to go back in your book and reproduce this proof tomorrow morning, you're going to get stuck. You're going to struggle. That's going to happen.
So
I cannot recommend enough to go, and the proofs that we do, try and reproduce them yourself. Because when you're first getting introduced to these things,
Makes perfect sense.
it makes perfect sense when I say it up here, and then you go and you sit down and do it on your own, and for some reason, it just doesn't make sense anymore. You're like, what was the trick? What did we have to do? What was this? And so in my classes, I have to go over the exact same problem like 3 times with the students.
Yep.
Geez, how many times did we go over proof by induction?
My class.
Your calculus class is what I'm
No.
thinking of. And discrete math.
Yeah,
Discrete
almost
math,
every
We
day
just have like 50 homework problems.
we'd have a homework problem of it, and you'd have to reteach it to me.
Induction.
Yeah. So it's going to make sense when I go over it up here. I can't recommend enough to go over and try doing these things yourself. Just look through the book, look for where it says theorem 1, try and prove it. Look for where it says theorem 2, try and prove it, etc. And then obviously you have online solutions if you get stuck, and if you want to dig through the video to find where we have it. Starts at 37 minutes in. Well, most likely not that, because you guys are so late. Anyways,
26,
let's start.
37 seconds.
So, proof. Gonna give you all my own style now. Y plus x equal to y implies x is equal to 0. 1. Let x and y be real numbers. Let x and y in the set of real numbers. That's how we read that, in. So let x and y in real numbers such that s dot t dot, we do that because we say such that so many times it's ridiculous, such that y plus x is equal to y. Right?
Yeah.
And we're ultimately trying to show that x is equal to 0. 2. So first I'm going to need my additive inverse for y. What axiom tells me that?
1.
Axiom, no.
No.
Oh, you're talking 4?
5.
4, it's 5. So then I might say, observe that by axiom 5, there exists z in the real numbers such that y plus z is equal to 0. You see how axiom 5 gives us that? Axiom 5 says for any real number you pick, in this case we have our y over there, I can always find a real number, in our case it's z, such that the sum of the two numbers is 0. So I'm guaranteed whatever this y is, that there is some other element out there, some other real number, call it z, such that their sum is equal to 0. Make sense?
Yeah.
All right. 3. Then x is equal to x plus 0. Told you, adding 0 sometimes is weird.
Oh, yes. Yes.
Is equal to x plus 0. Spelled it weird.
Right.
Put a t in the middle.
Right.
Is equal to, kind of just, as a general rule, we never really specify when we're using these two because they're used so much, or even this, and this, those 3.
Or all 3, all 12 of them, really.
Well, when we're getting introduced with the ones we're less comfortable with, sometimes we mention them as we're reusing them if it doesn't seem like it's obvious. But associativity, commutativity, and distribution, we do so much. You guys should have had so much practice in algebra now that going from this to this should be obvious. So you're good with this step to this step, right?
Yeah.
Nothing weird there. Doesn't matter where we put the parentheses. That's all I changed. And I might make a call back to our premise. Since y plus x is equal to y, then what we had so far, x plus y plus z is equal to y plus z is equal to 0. Therefore, x is equal to x plus y plus z is equal to 0. And we're done. And you put a little box at the end of your proofs. As a matter of convention, you used to put Q dot E dot D dot, which was an acronym for some Latin phrase that meant something to be effective, and thus it is demonstrated.
Fill that in.
And since drawing 3 themes took too long, we went to 1. A nice square. And a lot of people will fill it in.
What are you talking about? For therefore you draw 3 dots.
Yeah, there's other shorthands for therefore and other ones, but we won't do stuff like that. We're not that lazy. Jeez, James. Anyways, any questions about this proof? For those of you going into calculus or discrete math, this is roughly what I would expect from you if I had to prove this.
Right.
See you guys staring at it. It's,
I'm a little.
you just looking at it, you
Lost
find
on line
something.
4.
I'm missing line 4 just a little bit. Like the half.
Oh, I see. My callback doesn't work.
Second half of line 4.
So since y plus x, oh, did I have the wrong order there? I'm sorry. It's y plus x is equal to y, and I have x plus y, and then plus y.
Yeah.
That's
My bad.
That's not the confusion.
Actually, that threw me off hard. I was like,
Alright.
I really
We'll
can't
go
see
back
what
up
you're
here and
talking
we'll
about.
squeeze it in with one more step. So let's see.
Yeah.
X plus 0 was equal to x plus 0
Right.
was equal to x was equal to, well, we fit it, y plus x plus z. And now down here we can switch this to y plus x. Okay.
Okay,
How's that?
that's not the issue. That's
Huh?
not, that wasn't the issue for me.
I know that y plus x is equal to y. And I know that y plus z is equal to 0.
Yeah, that makes sense.
Oh, is this? So this last part's what was throwing you
No,
off?
that makes sense, yeah.
I think
Oh no, I'm good now.
I think your throwback is throwback. I think going back to, I think what most people did was they looked at how did you get from y plus x equals y, replace then for equal sign in their brain.
Oh, so
You know
you're
what I'm
saying doing this continuation
Yeah,
was
that
throwing
would,
off?
right. But yes, makes perfect sense.
Makes sense, yeah.
Alright. Any other questions? Anything weird?
Wait,
You're right. I don't think I could produce that. Reproduce it.
the whole thing's weird to me. Therefore, x equals x
So
plus y plus z. Where did we get that from again?
Yeah.
So, maybe I went too hard to do a throwback. So maybe you would have liked this better.
Wait,
Ah, come on, man.
no, we weren't that far. Need a little
Well,
explanation.
just watch what I do. Is equal to y plus z is equal to 0. Therefore,
Wait a minute.
x is equal to
Where
0.
did you get that?
Top line. The same.
Just continued.
Perfect. That makes
Y plus
perfect.
x, that's y. Z, that's z. Y plus z, that's 0.
Right, there you go. X equals 0.
Is that better? Or
Way
is that
better.
worse?
Way better.
I would have done it
What
that
was all
exact
this
way.
stuff? Why did you put that?
I was paranoid at going from this step to this step, I'd lose you.
He,
With the
he
X
did the
disappearing.
throwback. He did sin.
So I wanted to go back and re-mention this piece before I continued in this, but that seemed to just throw you off.
Well, I mean, Sense. I guess.
So having it one big string of equals
Really kind of
seems like it's better.
like it's the same, just shorter.
Well, yeah, it's the exact same logic. It's just expressed differently. There's no one right way to do the proof. Huh?
You're missing your
Did you go over these?
I do that
before
so
this class?
much. Sorry, what? Nothing?
Fill in your box.
Nah. See.
You never did that, ever.
Yeah, that's true. You never let us last that too.
Sloppy.
Get after you people that are obsessive compulsive.
That's the best part of a proof. That's the best part of a proof.
Okay, so we're good with this. Nothing weird.
Nothing weird.
You worried that you couldn't do it?
Yeah. Just take a picture.
Let's just go over in our head how we would do this real quick. If I saw that y plus x equals y, and I need to make this x equals 0, notice all I need to do is get rid of y on both sides.
Okay.
Like, think about how you would have done a regular algebra problem. If you would have seen x plus y is equal to y, and I said solve for x, what would you do?
Subtract y.
You'd subtract y from both sides. I did that exact same thing, so your intuition about how to do it is right. I said I need to add negative y to both sides. Right? But we don't have negative y yet. What do I have? I have a z such that their sum is equal to 0. Z is negative y in this case. So I took this equation and I added z to both sides. So I said x plus y plus z is equal to y plus z.
Y plus z is 0.
And y plus z is 0.
And x plus y is y.
And 0. So I get x plus 0 is equal to 0. That's exactly what we did in this proof.
That makes
So-
way more sense.
We start with, observe that there is something that is negative y. We're calling it z. Then, we're kind of working up like this, do. So we're going to go up, over, down. Make sense?
A little bit.
Look,
Well,
just-
look, you know that this is equal to this is equal to this, and this is equal to this, right?
Yeah.
And you also know that this is equal to this is equal to this, and that this is equal to this is equal to this, right?
Okay.
0.
So I can do this is the same as this, 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 is the same as this.
Okay, but just show him line 3, because line 3 makes perfect sense.
Well, that's exactly what I'm doing, line 3. So I'm starting
I
with
know.
x is x plus 0. Notice we could have simplified this one more time. It says x equals 0, right? So x is x plus 0, is x plus y plus negative y, or z, is, I just moved my parentheses because I'm getting ready to do my substitution. Oh, I didn't quite do what I said I did.
Yeah,
I lied, I didn't do that.
That's why I was confused.
Yeah, because y doesn't.
Okay, so, never mind on that, but same exact strategy. Same exact strategy that I realized I need to add z to both sides of this. I need to add negative y to both sides, and that's ultimately the realization to do the proof. So x is equal to x plus 0 is equal to x plus y plus negative y. Now I'm grouping my x plus y together so I can use my substitution up here. X plus y, I need to get a y plus x, because this is y plus x equals y, not x plus y equals y. So let's just change
And
the
you can
order.
just switch them around. Well, there's an axiom.
Yeah.
that says you can. Axiom 1.
X plus y is equal to y plus x. It's always the case for any two numbers. So it happens to be the case for whatever these two numbers are. Whatever those two numbers are, it's the exact same value as whatever those two numbers are. There's two different ways of writing the exact same number. X plus y is just a number, and it's the exact same number that y plus x is. And then do our substitution for y, and y plus negative y is 0.
What?
So your intuition about how to solve the problem is exactly right. We need to add negative y to both sides. That's it.
We just got to do that to do it.
Just got to do what to do it?
All of that.
Yeah.
But now we know we're wrong. The theorem, I guess.
Yeah, you have the theorem, but hopefully you would be able to reproduce the theorem once you understand it.
Perfect.
And now we're using real numbers. It's so exciting. We never actually have to draw that hard.
Oh,
It's
because
always
it's not
been-
a discrete
It's
set.
always been integers.
Yeah. So we good on this? Anything still weird? Anything feel unnatural?
Oh,
All right.
only the R.
You are very weird and you're very good.
What?
Said only the R.
Jacob said you're very weird. Something, something.
Yeah, I felt
Yeah,
politically just right, what I said. I haven't smoked.
Well, what?
He didn't say
Is it really not, or is he just saying that?
Jake,
We have
you
video.
heard- you heard Jake.
Yeah, yeah.
Oh. You two must be related.
Weird.
Yeah.
It's weird how
It's
zeros
distant
equal
when it's
zeros.
It's just. X times y equals y. And
Not gonna bother with that. Okay. So let's do the next one. So we've done theorem 1, now let's do theorem 2. What does theorem 2 say? It says if y times x is equal to y,
and y is not equal to
and y is not equal to 0, then, I'm going to say then, I should start with an if. If that's the case, then what are we saying? X is equal to 1?
Mhm.
Then x is equal to 1. Make sense what we're proving?
makes sense.
Mhm.
Okay, so let's start it. Now, thinking back to your algebra, if I had y times x is equal to y, what would I want to do to figure out what x is?
Divide
would
both
divide
sides by y.
I divide both sides by y. What's another way of saying that?
Multiply by 1 over y.
Multiply by the inverse.
Right.
So I want to multiply by the z, the magical z, that makes z times y is equal to 1. And that makes y times z is equal to
We
1.
have that, bro.
But don't you gotta switch to the right hand side? Well, I guess it doesn't matter.
Doesn't matter. But, so your intuition about how to do this algebraically is exactly what we need to do.
Isn't this basically saying that 1 is the identity element for
So this is very similar as the theorem 1, we're just
Yes.
basically doing
Just
Yes.
It's basically additive.
And we
Identity.
actually did this exact same thing with groups in general, with identity elements. But, so let's write this out. So let x, y into real numbers such that y is not equal to 0 and x times y is equal to y. Oops, y times x. Y times x is equal to y. Right? Setting up the problem. Maybe recall that anytime we have an if-then proof, you assume the antecedent and show that implies the conclusion, and you're done. We've been doing this over and over again with all our proofs.
Yeah.
So don't be confused by how we're doing an if-then proof. And not all of these are if-then, but these first three are if-then. They're implications. Same thing as an if-then, right?
Mhm.
Okay. So let x and y be real numbers where y is not 0 and x times y is equal to y. 2. Now I need to find that magical z such that y times z is equal to 1.
Observe axiom A6.
Observe that by A6, you said,
Yeah, there exists a z.
there exists a z
Oh, if y does not equal 0, I don't know if you have to
in
put that
R. We already know that y is not 0.
in. Okay.
There exists a z in R such that what?
X equals y times z.
No, that's not what
Y.
we want. You need to be just a little bit clever about how
Y
to use
equals
that.
x times z.
What am I going to write?
Y times x equals y times z.
Y times x times z equals
What do I need z to be? What's the property I want z to have?
1 over
You want
y.
z to be 1 over y.
I want it to be 1 over y, or I want it so that when z is multiplied by y, I get what?
Equals 1.
1.
1.
Yeah.
So, what am I going to write?
You can write that what you just barely wrote down.
There exists a z such that
3
X
times y equals 1.
y times z equals
1 is equal to
y times z.
y times z.
You can't just say that though.
Yes,
Yeah,
I
you
can.
Oh yeah.
So what does this say?
Any number.
This says for any number.
Bang.
If it's true for any number, it's true for 1.
Wow.
It's true for 1, it's true for 2, it's true for anything. So for any number you pick, as long as y is not 0, I can always find a z such that this product gives me that number. It also works for 1. Anyone still confused by how we can say this from axiom 6? Anything weird? You can reproduce that easy?
Not easy.
Easy peasy. All right. I know Peter wants to finish it from here, but I'm going to do it.
Thank you.
Okay. So,
Are we going to be proving some of these? Because that looks pretty fun.
Yeah, it does.
yeah, I wrote a bunch of exercises that I found afterwards, so you guys are going to do these ones.
Cool.
I just didn't want to tell you that because I didn't want you thinking about these while we're going over the rest of them. But now it's all you're going to dwell on.
Now that you say that.
No.
All right.
I choose 5.
So 3. What are we going to write now?
1 sec.
I'll give you a hint.
Y, then y times x equals.
I may want to start out with x equals blah 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 blah
Right.
1.
Right. X equals.
If only there was something.
Y
I could-
times z. X equals y times z.
Well, let's not skip to that. X is equal to x times 1 is equal to x times
Y times Z.
y times z.
Wow.
See, adding 0 and multiplying by 1 gets
off
tricky.
my game. I'm actually off my game because I should have seen that.
And I assume we all know how to do it from here, right?
Yeah.
Yeah.
So, ultimately, we got to group the x and the y together and get them in the right order.
Right.
I'm going to do 2 steps in 1. Don't let me lose you. Y times x
Wait a minute.
times z. Alright, so, and then we won't do a callback because I killed you guys last time.
Y.
Notice that y times x is y, so that's equal to
Y
Y
times z.
y
is equal to
times
y.
z,
Which is equal to 1.
Which is equal to 1.
which is equal to 1 period squared.
Wow.
Not
Bill,
billable.
I will literally
Okay, anything weird on that proof? Anything that doesn't make sense? Anything you don't like? Other than the not filled in square?
It's literally a not square.
A not square?
Yeah. I'm saying, unless it's not.
Okay, we're good?
We're good.
I'm erasing it. It's gone forever.
Yep. No video or anything.
No video or anything. And the author doesn't give you a solution in the book. Okay, next one.
The author doesn't solve these in the book.
No, he does.
No, it's just
I think.
Josh here.
I know he solves most of them, if not all of them. You might leave some as like, say, this is an exercise for student. So,
Yeah, those discrete math ones like that were frustrating.
if x plus y is equal to x plus z, then y is equal to z. And we prove this with groups in general, right? Remember that? Left-hand cancellation law? So now let's prove it in this very special case. How am I going to start?
Start with your for all x, for all y, for all.
By finding a number that's basically negative x. That's where it will go, but we're going to start by, we need to get two numbers, y and z.
What?
And x.
X,
Three
Y,
numbers.
Z, and
So let x, y, and z be any three real numbers on Earth you can think of. But they have to be on Earth. Anywhere higher, cut it. Such that x plus y is equal to x plus z. Alright, now we'll do what Emma was saying. We need to find a negative x. How do we get a negative x?
you.
4, 3.
No.
By A5,
Yeah.
Yeah.
there exists, U in R. We ran out of letters, so I said
A. Wait,
There
that's-
exists some number U in R, such that what?
x plus u equals
X plus
0.
That looks more like a mu.
I literally broke your
Not the
English.
right line. That's how I spell it. Okay. So there exists some u such that x plus u equals 0.
Yep.
So for any real number x you find, I can always find another real number called u such that their sum is 0. Make sense?
Yeah.
That's what axiom 5 tells us. Okay. Then what?
These are your questions.
You're gonna add 0.
I'm going to add 0.
True.
Then y is equal to y plus 0 is equal to y plus
X plus u.
0 is equal to
0.
y plus x plus
plus
u.
u.
You couldn't be more wrong. We need to change the order.
It's
I
equal
did
to
that
x
in one
plus
step.
z.
X
Donnie.
plus y plus u
Donnie.
is equal to
X plus z.
plus u.
Okay, yeah. Let's do that.
Is equal to
X plus u plus
Z plus
z
x
plus
plus
x plus u. That's a lot of steps in one. Hope you guys can keep up. Is equal to z plus 0 is equal to z.
u. Wow. That was pretty neat.
You can fill it in the square.
Kind of. I left some white spots just for you.
You usually do that.
Wow,
so it's
yeah.
Okay.
Only a scrub.
Any questions on that one? James? Do you have any questions?
Don't wake up us.
Okay. I don't want to wake you up. Be sure to whisper. Any other questions?
Are all of these gonna be 2
Yeah.
groups?
Why's your hand up? Put it down. Don't do that. That is messed up. You're gonna have to leave if you keep doing that. Okay.
It's an agile habit.
All right. Now I'll just erase it. Okay. So these are actually a lot easier than the other ones, I think, because our proofs with groups were more abstract.
Yeah.
So, did you guys want to try one?
Yeah.
Sure.
Okay, race.
Race?
Yeah.
You guys
Oh,
gotta help
maybe
me,
you
honestly.
might.
I'm just the scribe. Wait, you gotta define that first.
You're doing this one. X times 0 is equal to 0.
I thought we were on 6 if I was gonna be honest.
Oh, well, if you don't want to do it, you don't have to.
No, that's go ahead and do it. So
I'll let you go ahead and do it.
well then start like you should.
Yeah, what are we proving?
If this
It's
is
not if then. You're just proving any number times 0 is equal to 0.
Well, I'll just do this. From x there exists
In R.
in R. There exists or
I'm not
then x times wait.
We're not doing this then.
Let x be a real number. Just pick a number out of there. Alright, now you're proving that that thing times 0 equals 0 and you're done. Timesing by 0 is hard.
It's the same thing as timesing by.
I
Zero.
keep thinking timesing by 1.
No, multiply by 0. See if you can figure out how to write 0.
X times 0.
You need a t in the middle.
Be x plus y, or y is negative x.
X plus 0.
What?
You need
Why
to
say
you need to
X
let
times y, or x times 0 with the t in the middle.
Can you guys pick up on what
their-
you
So
said?
we need to write there exists y such that x plus y is 0. And then multiply it by x plus
Okay,
y.
which theorem are we using?
I would look at axiom 3.
3, not 2.
Oh.
Not axiom 5. Don't you need 5 and then 3?
That makes
I'm
sense.
sure there's tons of ways to do it.
Oh, I don't know.
So you're saying observe five.
3.
I wasn't talking about 5.
No.
You're following me by now.
I don't follow me.
I would say observe 5.
Okay.
There exists. I know I'm sloppy if I'm doing this imprecise. There exists y.
Such that x plus y equals 0.
This would probably be easier to do with,
Okay.
with 3 now when I look at it.
Well, I need a 0. I need to work with the 0 and I need to find
You
ways
can do
to
it with 3.
So what if we said,
With 3 you just
what if
say,
we said x times 0?
Don't you need 5 and 3?
no.
X times 0
Equals
equals
x plus y.
x times x plus y. I don't know where we're going.
If you use 3, you can go let y plus, you just show them
You
y
know
plus
what?
0.
Well.
You don't have to, oh, you do have to distribute property. X times x plus x times y.
Yeah, that distributive property is a very nice one. Especially because it has a t in the middle.
You are so stupid.
Try x times 0 plus 0.
Equals x times 0 plus x times 0. Okay.
You said that?
Well,
You gotta go back to
there you go. Woo. Makes you feel alive, doesn't it?
No. No.
Well, you know that.
one more step.
What is it?
Okay, so I'm looking at A2. Watch. Maybe I should go to that. A3.
Maybe start out with zeros equal to 0 plus 0. And then multiply both sides by x.
You're saying 0 equals 0 plus 0.
Now multiply both sides by x. No. Yeah, multiply both sides by
I
x.
did. I just did it in my head.
So you start out by
Okay.
saying,
That's
observe
You
that.
distributed already. Right?
Yeah.
Okay, you're so close.
You're basically done. That's it. You just gotta go backwards. You say observe that 0 equals 0 plus 0.
Then you multiply both sides by x, and
Yeah.
then you distribute, which is where he's at. Now one more step. Well, 2 more steps.
I can't undistribute.
No.
No.
Where are you trying to get?
0. I'm trying to get x equals 0.
So,
Oh, I'm trying to get x plus 0 equals 0.
you're trying to get x times 0 equals 0. Or 0 equals x times 0, based off that habit.
0 equals that, yeah.
Can you? No.
How many zeros can you add to the left-hand side?
What is your problem?
As many as you want. So
So
what?
you can do at least one, right? What did you put there?
X times 0.
No, just put 0. There's a way easier way to write 0. There you go. No? Well, okay.
0 plus 0, is that what you want?
No, just 0, exactly like you have it. 0 plus x times 0 is equal to
Oh!
x.
Now we have, where is it? 5? No. 4. X plus 0 equals x. So, x, maybe I'm way off.
Well, that's what you just
0.
used to add the 0.
Huh?
That's when you just used to add the 0 there.
Not multiply it.
You took x and you rewrote it as x plus 0.
Oh, you're
Yes, you just use that. Now what do you want to use?
plus x plus 0.
Don't look at theorem 3.
Okay. Distributive property?
No, theorem 3.
Oh.
Yeah, that pretty much does it.
So
doesn't
that makes 0 equal x times 0.
There you go. Now erase all that and write it out good.
Excuse me, Potts. Okay.
Yeah, just,
Okay.
oh yeah.
0 equals.
Observe that. 0 equals 0 times 0.
Wait, are you starting out with a 0?
X times.
No.
No,
Start
0
with
times
0 is equal to 0 plus 0. Wonderful. Now, then you multiply both sides by x.
I know.
Okay.
implies that.
Oh, is that implies?
Equals.
No, not equals.
Oh, you
implies
write
that.
equals. Yeah, no, you can't do equals.
It doesn't equal.
You're
it
assuming
implies.
your
You're right,
proof
you're
when
right.
you do that.
Okay.
Can other people see if you're doing it right?
He's doing it
Because
right.
I can't see it from here.
Start over here. Why is that?
You following this, James?
I'm following his handwriting, that's for sure.
You're doing exercise 1, just so you know.
Oh, scary.
And it is the hardest of those exercises.
Yeah, to begin with.
Probably
Sure.
use it for the rest of them.
Should I write the axiom I'm using or just go ahead?
As long as the people watching you understand what you're
Levi
doing.
understands.
Well, we just barely did the entire.
Levi
proof, so
understands.
we
Yeah,
should all
sounds like you
understand
reached the whole class.
The whole class.
Do you have it?
Let me.
This is by a.
Wait, how'd you add 0?
As you can see, I had a wonderful time reading Jacob's homework.
So this one is by theorem 3.
Are you the one that always uses
So-
You gotta name the axiom you're using
Okay.
in the theorem.
Okay. We will go to here then, because of you guys. 3. Then by theorem, we'll erase that. 3, comma 0 plus that equals x times plus x times 0 implies 0 equals x times 0. Ooh.
Alright, so let's go over and make sure it makes sense. So, there's a let right here. So let x be any real number. Where we're starting. Now we're saying that, observe that 0 is equal to 0 plus 0. How do we know that?
Well, because
It
it's
just happens.
No, nothing just happens.
4.
That's a consequence of theorem 4, or axiom 4. Axiom 4 says that anything plus 0 just gives you that thing. Or take anything you want, you can add 0 to it and you didn't change it. So we're doing it this way. We're saying 0 is equal to 0 plus 0. If it's true for any real number x, it's true for 0 as well when you plug in 0 for x in it. So that's how we're getting this. Now, he's going from this to multiplying both sides by x and then distributing, so let's rewrite this. His middle step is going from this to, then x times 0 is equal to x times 0 plus 0. How do we know that we can do that?
there's another one of those. Is it 3?
No.
No, that's the next step.
It's
Identity, logic thing?
Yeah, it's a rule of logic.
Oh yeah.
right.
For any operation you're talking about, if I have two things that are equal, and I apply that operation to those those things are still equal. Make sense?
Mm-hmm.
And then we get from here to here. How do we do that?
That's axiom 3.
That's distribution. Yeah, axiom 3. So from here to here, we used axiom 3. And then, from here to here, what did we do?
Use axiom 5. No, sorry, axiom 4.
Is that the one that says you can add 0?
Yep.
Yep. So once again, we know that we can take the left-hand side of this equation, add 0 to it, and it's still a true equation, which is what I did here. And then we're using this theorem. Theorem 3 says, if I have the same thing, well, what's the right way to say that? Just say how it is. If x plus y is equal to x plus z, I can cancel out the x's from both sides, and I'm left with y is equal to z. Same thing here. If
Y plus x.
If y plus x is equal to y plus, oops,
Y plus
Yes.
x is equal
if
to
y plus x is equal to z plus x, then y is equal to z.
Yep.
Yeah.
So I can cancel out that on both sides.
Uh-huh.
And so then I'm left with, then I'm left with this,
Yep.
which is what we were trying to prove. So, any questions? You good?
Yeah.
Now I'm erasing it.
Well, I understand the whiteboard perfectly fine, especially when it's clear.
All right.
You understand?
Okay. So the next one. So we knew as an axiom that for any x there is some y such that their sum is 0. Now we're going to show that for any x there's only one y such that their sum is equal to
I don't
0.
know how you're going to prove that, honestly.
It makes sense. Well, you use it as
Oh, by way of
right?
contradiction. You're going to assume something.
Yep, that's one way to do it. Or you could say let y prime also satisfy the property and show that it's equal to y. But
All right.
Isn't
You did
that
with
basically
I
the
think-
same thing as proved by contradiction, though? Basically.
no.
No.
It's showing that anything that has that property is equal to y.
Okay.
So if you look at the set of everything that has a property, that set is just y. But we'll do proof by contradiction because I think it's the more intuitive way to do it.
Yeah.
So that's what we're doing. Alright, so we're proving that there exists one and only one y in R such that x plus y is equal to 0. So let x and y in R such that x plus y is equal to 0. 2. Assume by way of contradiction
There exists.
that there exists y prime. We're not doing any operation, it's just a different variable. I guess none of you have done calculus, so you have. But, so we're just talking about a different variable, we're not talking about a derivative or anything. So, assume by way of contradiction that there's some y prime such that x plus y prime is equal to 0 and y is not equal to y prime. So we're saying, huh?
What is y prime?
It's just some other number that when you add to x you get 0.
Doesn't
There isn't one.
Yeah, it doesn't
So
exist.
what we're trying to prove is that, so if we're talking about 3, we're saying the only number that you can add to 3 to get 0 is negative 3. We're saying that there's one and only one number that does that. How are we proving that? We're going to say, assume that there is some other number out there, call it y prime. I don't know what it is, but let's pretend that there is some other one, and show that that leads to an impossible worldview. It's not possible for there to be more than just negative 3, so there is just negative 3. Okay. So assume by way of contradiction that there exists some other y prime that satisfies this condition, and it's a number different from y. Then x plus y is equal to 0 is equal to x plus y prime, which gives us y is equal to y prime, contradiction.
I was ready for something real good. What?
Right?
That was pretty simple.
X plus y is equal to 0, x plus y prime is equal to 0, therefore x plus y is equal to x plus y prime. Apply theorem 3 means we can get rid of the x on both sides. You're left with y is equal to y prime. Contradiction, because we said assume that y prime satisfies this and it's not equal to y. And it is equal to y. y not equal to y and y equal to y is a contradiction. It's impossible for that to be true.
Well, why not?
So it's impossible for y prime to exist. So there is no other number out there other than negative x that makes this true.
Don't you also have to prove that y does exist?
Now we know that a y exists. That's what the axiom gives us.
That's right.
So it tells us that there's at least one, and and there's also at most one. Therefore, there's one and only one. Good. Okay. So now we're going to do a definition, and you'll notice that definitions usually come right after proofs like this.
Why?
So we'll speak kind of high level about defining something.
There's only one.
Yeah, we need to make sure that there's only one before we make a definition. So now I'm going to call whatever this one and only one y is that I can add to x to get 0, I'm going to call that thing negative x.
Right.
And negative x only makes sense as a definition of a number if I'm only talking about a number.
So that's basically defining a negative number.
This?
Yes.
It's setting us up.
It's saying definition 1 is defining a negative number.
It's exactly what it's doing. So definition 1, now we're defining this symbol negative x. Notice everywhere before here, not once do we have the negative symbol. We've never talked about a negative number. We've never had a negative number. This is the first time that we're ever introducing the symbol. And we're telling you what it means. What do I mean by negative x? I'm saying negative x is that one and only one y such that x plus y equals 0. It's the one and only one number that when I add to x I get 0. That's what negative x is. That's exactly what we mean by negative 3. What is negative 3? It's the number such that when I add it to 3 I get 0. That's what negative 3 is. Right? No confusion there?
Nope, none.
Okay, now let's do the dumbest theorem in this whole book. I don't like that he has this as a theorem.
Why is that? Yeah, why is that even?
He says x plus negative x equals 0.
That's basically the definition.
That's the
Isn't it?
definition, isn't it?
Exactly. How does he do his proof? He says, observe that negative x is equal to negative x,
Wow.
which satisfies this, therefore it satisfies this.
Observe.
The reason I don't like that he does that is because he's doing a proof that only references a rule of logic to prove it. And I think that that's a terrible, terrible thing to do to students because we're looking at the logical implications of these things. Anytime we use logic, that should be behind the scenes. We shouldn't do a proof that explicitly just relies on a rule of logic. So if you're looking at this and you're saying, isn't this just using the definition? Yes, this is just using the definition. Make sense? So we're all good with this? Do we need to write out the proof?
No.
All right. So now we'll go to 7. Seven. So we're proving that the negative of negative x is equal to x. 1, let x be any real number, it doesn't matter. Now what is the negative of negative x?
Just negative subnumber.
What is this number? What is the special property that this number has?
It's that number plus another number which equals 0.
What other number?
What?
X.
No.
Negative 1.
Negative x.
Oh.
Negative, this thing, is the number such that when added with this thing, you get 0.
Right.
Don't be thrown off just because whatever we have in there happens to be a negative number. So I know that
When you add negative x to
negative x plus negative x is equal to 0.
Right. Right.
Is there anything weird about this line here?
No, makes perfect logic. You just
Negative. Did I write it in the same order that we do over there?
No.
Let me write it how we write it over there. Using this right here. What am I plugging in for x? I'm plugging in this thing, negative x. That plus, I'll write it this way, we're going to have to use brackets. Sorry. That's plugging negative x in for x here.
Uh-huh.
This is true for any number x I pick. Is negative x a number? Yes, then I can plug it in here.
So where do we prove that negative x is logically equivalent to negative 1 times x?
That's for right here.
Oh, I didn't see
And
that.
that's what James is doing.
That's the hard one.
So he'll show you that. Oh yeah, that one's gonna be a pain. Don't know how he's gonna do it.
Which one?
One on the exercises.
The only
Okay. So everyone's good with this line. Perfectly valid to plug in negative x into this. You can plug any number into x here.
And then that's just the negative of negative x.
The x here and the x here have nothing to do with each other. This is a dummy variable.
Oh, no, I'm talking about the next one.
Oh, yeah, this is also equal to, how else can we write this?
Right, because of definition 1.
Right?
Mm-hmm.
No, you can't actually.
Uh-huh.
It's not what it says.
X plus negative x is equal to 0. Every time. That's exactly what this says.
Oh, yes.
Any number plus its negative is 0.
Yeah.
That's true when I plug x in there. That's true when I plug negative x in there. That's true for anything I plug in here. Is there anything confusing about this? Anything you don't like? Anything you love?
It makes
I wouldn't go
sense.
that far.
Nothing you love? If you don't love all of it, you're doing math wrong. Anyways, now we can use the cancellation law, right? This cancels out with this, and that gives us, that implies that negative x is equal to x. And we're done.
Good job.
Oh, wait,
yeah.
10 seconds.
Alright, good. Only took half a second.
Why'd you ask for a minute?
Oh, yeah.
Okay.
Just in case.
Follow me on? Negative x times y is equal to negative x times y.
That's going to be tricky. Seems like you used 1 before you did it.
Seems like you use example when you
Well, let's start with what we need. Negative x. I'm not going to put the y in parentheses. Everyone okay with this?
No.
Everyone okay that this is saying the exact same thing that last saying?
Mm-hmm. Well, you could put parentheses around that other example.
Okay, so you're not?
Well, I mean, don't you need to?
No. It's negative the symbol I have here, which is just x times y.
Yeah, but with the order of operations, you usually use negative x times negative x.
I guess you could, yeah. Alright, we'll put the parentheses.
Got it.
Okay. So, let x and y be real numbers. Oops. Let x and y be any real numbers, doesn't matter what they are. Then, let's see how we want to do this.
Just start with your left and make it the right.
Then, what would I get if I did y? Minus y. Do I like that? X. Then, let's see, if I have y times x, we don't have minus y yet. How am I going to get my x, y? Plus y.
Use the double negative x, and then change the negative x to x.
I need to get something like, so I'm trying to think how to get here. I need x times y plus negative x y is equal to x times y plus negative xy. Sorry. Shouldn't have written that quote over there. Let me write y math one more time. So I'm trying to get something to the effect of x times y plus negative x times y is equal to x times y plus negative x times y. Let me just see this. Then let's see, negative x times y is equal to oops, negative x times y, let's just do plus x times y is equal to, let's take the y out of there. Oh, there we go. Okay, I got it now. Let me write it this way. I see how I'm doing now. Okay, so we have y times, I guess it's in that order, sorry. We'll just do a couple more steps. Okay, so negative x times y plus x times y is equal to y times negative x plus y times x. You with me on that? Just reordering things?
Yes, but
Now I'm going to factor the y out. Y times negative x plus x is equal to y times 0 is equal to 0. Anything weird in that?
oh, you just proved it. There you go.
Yeah, therefore, negative x times y is equal to negative x times y.
Okay, I was really confused because I was like, I don't understand how you're just adding x times y to this. So
You can add on both sides.
So here's the thought process. Sorry, I'm going down that track, probably three off what I was after. So remember, what do I know about this number?
It's the opposite of x.
This is the one and only number such that when added with x times y equals 0. So if this number, when added with x times y, gives me 0, then these two numbers have to be the same. There's one and only one number that I can add this to, namely this number. Oh, sorry, I said that backwards. There's one and only number I can add to this, namely this number, such that their sum gives me 0. When I added this number, their sum gave me 0. Therefore, this number and this number have to be the same number.
Okay, so that doesn't make sense to me. Yes, it does.
Yeah, it makes sense.
I mean,
Kind of roundabout.
we could have gone to this.
No, that actually makes perfect sense.
Is equal to 0 is equal to negative x times y
Plus x times y.
plus x times y. And then that gives us, using cancellation, so I know that this is equal to this, cancel those out, and that gives me negative x times y is equal to negative x times y.
Yeah.
And that's another way we could have done it.
Well, it just names the lost step, makes it look more clear.
Okay. Now that one doesn't. That way of proving it doesn't make sense to me because
Does it make sense to you up to here?
yes,
Does
the
it
other
make
way
sense?
made perfect sense.
Okay. Does it make sense that this is equal to 0?
Yes.
Okay. Does it make sense I can cancel out that with that?
No.
Okay, let me.
Yes. Yes.
Okay.
No. Just because you're taking it all away and then you're saying it still is equal. So that's just throwing me off.
So you've got that this is equal to 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 this.
Yes.
So then, negative x times y is equal to negative x times y. Oops.
Just leave that.
Sorry.
Because that makes sense.
Then, negative x times y plus x times y is equal to negative x times y plus x times y, which
Okay.
then gives us
You had me.
negative x times y is equal to negative x times y.
Mm-hmm.
Is that better?
Makes sense to me
Your first way made the most sense, but yeah.
Yeah, I think.
That makes
But
perfect
does
sense.
this one make
Yeah,
perfect
it
sense?
makes sense.
Anything weird? Anything that doesn't make sense? Huh, James? This is the trick, by the way, for proving this one.
Thanks for that tip. It's good to know.
I could probably prove
So is the next theorem, by the way, and the one after that. You follow it?
I'm pretty sure.
How do you?
You're pretty sure? You should be positive. So what's making you
No,
only
I
pretty?
gotta prove stuff that's negative. I can't be positive.
Negatives can't be positive.
Wait a minute.
Here's just what we're starting with.
Mhm.
Ultimately, what am I trying to do? I'm trying to show that this is equal to this. Right? So I start out with this, and what I'm thinking is ultimately I'm going to have to get this is equal. I'm starting out with this. I'm going to need to show that that's equal to this. Then I can cancel out the x and y, and I've got what I want. Okay? Because these are both just 0, which is what I'm going to show. So we start out with negative x times y plus x times y. This is just what we start with, and we're going to keep messing with this until we ultimately get this. So negative x times y plus x times y. I just reorder things. Didn't do anything else, just reordering.
Mhm.
Factor out the y. What's negative x plus x?
That's 0.
0. So we get y times 0 now. And y times 0 is 1 minus 1. You follow me? Okay, 0. And 0 we know is also equal to x plus negative x. Or x times y plus negative x times y. Right? You're used to seeing those in the different order, but it doesn't matter. So we got this, where we started, is equal to where we end.
Mhm.
We started here, we ended here, all equal. So we got this is equal to this. Cancel out minus x times y from both sides if you want to think about it that way. We have our cancellation. We can cancel the x and the y and the x and the y. So I'm left with just this piece is equal to just this piece. And we're done. Make sense?
Mhm.
Good?
That was tricky.
Super tricky. Fell right to the floor.
A whole 2 steps.
Okay. Next one. We want to show negative y is less than negative x if and only if x is less than y. Okay, so for those of you who don't have a lot of experience proving before, if and only if proofs we break down into 2 steps. Because what does if and only if mean? It means if this is true, then this is true. And if this is true, then this is true. So we're proving 2 conditional proofs. We're proving this implies this, and this implies this. So these if and only if proofs are typically 2 proofs combined into 1. So let me show you how we typically do this. So 1, start out just getting the stuff I need for the 2 proofs. And what do I need? I just need 2 real numbers, x and y. So 1, let x, y, in R. Okay, now we're ready to get started. 2. So which way should I prove first? Should I prove that if this is true, then this is true?
Yeah.
Or, okay, so we'll start with that. So if that's the way that we're going to start the implication, we usually do a little parenthesis, a big arrow showing which way we're going to do. So I'm saying, warning, we're doing an if and only if proof. I'm going to start by showing that this implies this. And I start by assuming my antecedent, and I need to use that to show my conclusion. So assume.
Tried to swear on us, though.
minus y is less than minus x. Okay, so when I have an inequality, what can I do to both sides? I can add whatever I want.
Add 0 maybe.
No, we don't need to add 0 this time.
Fine, add x. Fine, add
So assume that,
x plus y.
then we're going to add x and y to both sides.
Yep.
Got
Then
it.
negative y plus x plus y is less than
Oh, that's
negative
smart.
x plus y,
That was cool. That was cool.
right? We added the same thing to both sides,
Cheat hacks.
and that gives us, let's see, negative y plus x plus y is going to be x. Negative x plus y is going to be y.
Cheating.
Yeah, we cheated there. Can anyone see how we cheated?
By using our assumptions.
By being smart.
By being smart. He's got it. Okay. So we're done with that way of the proof. We showed if this is true, then this is true. We showed that way of our implication. Now we're going to show this way. So we do parentheses, arrow pointing this way to let us know, okay, we're done with that way, now we're showing this way. And we're going to start with the same thing, assume x is less than y. Now this one, we need to go the other way, so we can't just add to both sides. We need to somehow take away from both sides. And we can't do that.
Define your negative.
We don't even need to define our negative now, we have a definition.
That's what I'm
So what
saying.
are we going to do?
We don't need to define a negative.
Then x plus
Negative x.
negative x plus negative y is less than y plus negative y, negative x.
Are you using the same axiom to do that?
Yep.
I see. Yep, exact same axiom.
This is an easy one.
Here's an inequality. I can add the same thing to both sides. Doesn't matter what it is. That's a number, right? That's the same number. So I added the same number to both sides, which gives us, once you simplify, negative y is less than negative x. And we're done. Beautiful voice. All right.
What it means actually. 0 equals negative 0.
So we're done? No questions there? Everything makes sense?
Look at this next lemma. 0 equals negative.
Yeah, 0 equals. So the author
No.
goes from this to this, and he just proves this, similar to how we proved this. And I thought if you just add this lemma, then 10 is just a corollary of 9. So the author doesn't do this, but I figured let's just do that, and then this is just a corollary of this when you plug in 0 for y. Right?
Yep.
So let's do the lemma real quick. Lemma 0 is equal to negative 0. How are we going to prove that 0 is equal to negative 0?
Definition.
You're gonna add something.
Add 0 to both sides.
Observe that 0 is equal to what?
0 plus 0 equals 0.
0 plus 0, but that doesn't get us anywhere. We
Equals
need to negative 0.
Equals 0
plus negative 0. Right?
Yeah.
0 plus negative 0 is 0.
Yeah.
Which is equal to, if we want to
0.
use our axiom, negative 0 plus 0 is equal to negative 0.
Yeah.
So 0 equals negative 0.
Crazy.
1 second.
Yeah.
Seems like
I'll give you
it's-
3.
Seems like
Replace all your
Okay.
zeros. Replace all your zeros with the number 1.
Any number plus its negative is equal to 0. Doesn't work with that.
Huh.
1's not equal to negative 1.
You use 5. You use 5. Okay.
Right.
That's
So
where I
any
go.
number plus its negative is equal to 0. Right? Now 0 plus, the sum of any two things, we can change the order, right? And then anything plus 0 is just that thing.
Is
Okay.
negative
For a
zero-
second, I did not realize you
is
used
negative
That's so
zero
messed up.
considered a number?
What?
It's for that. Throws you off.
Is negative 0 considered a number?
It has to be, otherwise this doesn't make sense.
weird.
Or, sorry, go back to this axiom. Where are we? This axiom. This axiom says for any x there exists a y such that x plus y equals 0. That has to be true for 0 as well.
Well, y could just be 0.
It could just be 0. And it is just 0. So when we have this special additive inverse for it, what is the magic number that when I add to 0 I get 0?
Negative 0.
Negative 0, which we just showed is also 0.
Wow.
The additive inverse of 0 is 0. That's what we showed.
Beautiful.
Take the additive inverse of 0, which is negative 0, and what is it? It's 0.
So, okay.
So now you know 0
Now we
equals
know
negative
so
0.
much. We know so much.
Somehow, some.
Yeah.
0 plus 0 is actually 0. Wow.
You guys were catching up with kindergarten.
I don't know, man.
No, but
Those kids know some stuff. Alright. So that's lemma, and then
10's just a corollary.
10 is just a corollary of 9 now. Just plug in 0 for y. Plug in 0 for y here, and you get this.
Yeah.
Okay.
Everyone see that?
Yeah.
Well, what about this? When I plug in 0 for y, I get negative 0.
What's your point?
Negative 0 is just 0.
Crazy.
That's my point. That's why we did that corollary. Okay. So we don't need to do 10, or we do need to do 10?
No, we're good with 10.
You good with 10, James?
I'm not good with 10.
You think you can prove that one?
No.
Yeah.
You couldn't prove 10 using 9 in this lemma?
That's pretty simple.
Yeah.
Okay, then we better write it.
Oh
Oh no.
Oh, yes.
So we're going to prove
Yeah.
that,
Yeah.
no. I don't think they get it.
Peter volunteers.
I don't volunteer.
we're going to prove that 0 less than negative x, if and only if x is less than 0. Right?
Yeah.
That's what we're trying to prove. Observe that,
Whoa. Aren't you supposed to say let?
nope, observe that negative y is less than negative x
I think yeah.
if and only if x is less than y.
I think that's equivalent to.
That's just theorem 9. We already proved that.
Oh yeah.
2, let y equal 0. 3, then we have negative 0 is less than negative x if and only if 0 is, x is less than 0. Right? Just plugging in 0 for y, and then using our lemma,
You said 0 is negative.
negative 0 is the same thing as 0.
Wow.
0 is less than negative x if and only if x is less than 0.
Okay.
You see it? All we did was took this, plugged in 0 for y, used the fact that negative 0 equals 0. You think you can do it now?
At home I couldn't.
What happened to you? You proved far more complex stuff than this in calculus. Just being out of school for someone's broken you?
Uh-huh.
Oh no.
Well, you should probably get that fixed.
I know, right?
Just watch the videos of calculus or read over the homework. Redo it. Help yourself. Okay,
Building up to today.
theorem 11. Yeah, we're proving it. We're working our way up to a definition for
Subtraction.
minus, subtraction. Yeah. So, we know that for any x and y, there exists a z, such that x is equal to y plus z. Now we're going to prove that there's one and only one z that makes that true. Does that make sense?
The exact same way we did one.
We could. Let's do this one the way that we don't do proof by contradiction, so that we can just.
The hard way.
Assume that.
It's actually simpler in writing, less writing, but just to see both of them. Alright, so prove, what are we trying to prove? We're trying to prove that there is one and only one z in R such that x is equal to y plus z. Right?
Okay.
1, let x, y in R, x, y, z in R such that x is equal to y plus z. 2. Let z prime be any number in R that happens to satisfy x plus y, that happens to satisfy x is equal to y plus z prime. So let z prime be any number in R that also happens to satisfy this. We're going to show that z prime is equal to z. So in other words, anytime you pick any number in R that satisfies this relation, you pick z. You pick it every time. Does that make sense?
Well, my only problem with that not making sense is you say the same exact thing for z, the same exact thing. There exists z in the rational such that for any time x equals
So,
y.
We are guaranteed that there's at least one number z such that x is equal to y plus z. We're guaranteed that there's at least one.
Okay.
Now we're saying, let's grab another one. I'm going to say, yeah, that other one that you grabbed, it turned out that was just z again. Because that's the only one that does it.
Right.
Does that make sense?
Yeah.
It's kind of like saying, let n be an even prime number. Well, then it's 2.
Right.
Anytime you grab an even prime number, you grab 2. Anytime you grab a z in R such that x is equal to y plus,
You grab z prime.
or anytime you grab a z prime in R such that x is equal to y plus z prime, you grab a z. Same thinking. Make sense? Alright. It's a lot of nodding. Okay. 3. So now we want to show that z is equal to z prime. So then,
You can do it the
Oh.
same way.
maybe this one doesn't work as good as that one. Maybe it does. Then z is equal to z plus 0,
Okay.
right?
Yeah.
Is equal to z plus y plus negative y. Oh, we never got x. Oh, I'm getting there. Z plus y is equal to x.
So you rows go first, but because
So this is equal to x plus,
confused at where
negative y.
directions go.
and then x is also equal to y plus z prime. Y plus z prime plus negative y is equal to, hopefully you can see the algebra on that, z prime.
Couldn't you just substitute? Seems like you go y plus z equals x equals y plus z prime implies that z equals z prime.
Yeah, we could have. It just would have been one line of equations. It would have been a line of equations implies some other equation.
Right, but it would have been shorter.
Yeah, probably. Any questions on it? Go over it one more time. Z is equal to z plus 0, right? We rewrote a difference, z plus y plus negative y. That's the same thing as that, right? We know that z plus y is equal to x. And we know that z plus y prime is also equal to x. So we took that, substituted for x, substituted for that. So we know that this is equal to x is equal to this. Combine the y and the negative y, and you're left with just z prime. Therefore, z equals z prime. Therefore, any number that satisfies this is z. So z is the only one. Good?
Great.
I don't think the logic is as good as doing a proof by contradiction, but it is another common way that this is proved.
Why?
But we could,
Why is it not as good as proof by contradiction?
I don't think it's as good as proof. I think the logic of proof by contradiction is clearer than, look, anytime we grab something that satisfied this, it was also z.
Yeah, I mean,
Okay, so we're good on that one. Now we're on theorem 12.
no,
Definition 2.
Oh, definition 2. Oh yeah, so we found out there's one and only one z that equals this. That makes this true, sorry. Z is the only number that when you add to y, you get x. So now we're going to come up with a special name for that z. we're going to call z the difference of x and y. Whatever the z is, that when you add to y, you get x, we're going to call that z x minus y. It's a new symbol. What does x minus y mean? It means that special symbol z, such that when you add it to y, you get x. That's what it means.
That is what it means.
We're defining what this means right here, right now. Ignore everything you know from the past.
That's the actual.
We are now defining this symbol. This is one way to do it. So typically you see it defined, I shouldn't say typically. The way I've usually seen it defined is like this, and then you prove this as a theorem. But you can define it like this and prove this as a theorem too. It's logically equivalent.
If and only if.
Okay.
Okay,
Right.
so z is that one and only one number such that when you add it to y, you get x. Or we're going to say that z is the difference of x and y. Everyone good with this line?
Mm-hmm.
X plus y, or y plus z equals x, if and only if z is the difference of x and y. Okay, so now let's do how we're used to saying it. We're saying what's x minus y, we're used to saying that's x plus negative y. We need to prove that's the case, and then we can start using it from there on out. Okay, so we're proving x minus y is equal to x plus negative y. 1. Let x and y let x, y, and z in R such that x is equal to y plus z.
Okay.
Good with how we're starting? We're just starting with this right here. Then I'm going to take this equation, I'm going to add the same thing to both sides. Then x plus negative y is equal to y plus z plus negative y. You good with that?
Yeah.
Yeah.
Is going to give us, I'm going to flip it as I write it, so see if you're okay with this. Z is equal to x plus negative y. Is that too big of a leap? Or you see that?
Too big.
That makes
Too
sense.
big? Y and negative y is?
0.
Sorry, yes.
Everyone see it?
Uh-huh.
You see it, James?
Mm-hmm.
It sees you. Okay, so z is equal to x plus negative y. Maybe we could say, put a little bit more explanation here, even though we're done. Therefore, z is equal to x minus y, and z is equal to x plus negative y, or in other words, x minus y is equal to x plus negative y.
Z is not equal to x
You
minus
get that by
y.
using the definition.
Yeah, it is. If x plus y, or if x is equal to y plus z, then by definition, z is equal to x minus y. That's what z is. So we already, I probably should have specified that here. Let da 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 da, comma, making z equal to x minus y.
Yep.
Maybe that helps clear it up. So I set it up such that z is equal to x minus y, and I go through the work of showing that z is also equal to x plus negative y. Therefore, those two are equal. What?
He was just shaking the table.
I
just
Oh.
Chase the theorem.
Is it still pointing good?
Probably.
What are they about us?
All right. You can just separate those
We're
two.
gonna have time to do these exercises.
Yeah, this is taking a little bit longer than I thought. Okay, I'm going to stop writing out full proofs and just give you the gist of it so that we can get to exercises. So, let's do this one. Prove that x is not less than x.
Wait a minute.
Or in other words, x is not less than x. By way of contradiction, let x less than x. Well, we know over here if x is less than y, then it is not the case that y is less than x.
Right.
So, x less than x implies
No.
x is not less than x. Contradiction. Good?
Yep.
What?
If x is less than y, y is not less than x.
Okay.
Alright, next one. I didn't specify this one very good. The theorem said prove that one and only one of these is the case. Okay?
Right.
So first off, right out the door we know x is equal to y or x is not equal to y, right?
Right.
Either a statement is true or its negation is true. So one of those two has to be true. That's the definition of a contradicting statement, right? And now we know that if x is not equal to y, then x is less than y or y is less than x. So we can rewrite this as x is equal to y or x is less than y or y is less than x.
Proved, brother.
No, we haven't proved it.
Yeah.
We've proven that at least one of these is true. Now we need to prove only one of them is true. Another way that we can prove only one of them is true is show that anytime two of them is true, we get a contradiction. So no two of them can be true, and we know at least one of them is true, therefore one and only one is true. Does that make sense?
Yeah.
They're like,
So we're going to take it one case at a time. There's going to be three cases. Assume two of them are true, get a contradiction. So let's assume x is equal to y and x is less than y. What do we get?
If x is
Oh,
equal to
sorry.
y.
And it doesn't even...
that's the contradiction.
So if x is equal to y and x is less than y, then we get x is less than x. Contradiction.
Oh, right.
Because identity. If x is equal to y, plug in x for y, you get x is less than x. Contradiction. We already know that's not the case. That was a previous theorem.
Same thing happens with the
Same thing with the next one.
Yeah.
2. If we assume x is equal to y and y is less than x, we get x is less than x.
Crazy.
Contradiction.
Uh-uh.
Okay, finally, the third case. Assume x is less than y and y is less than x. Well, x is less than y implies that y is not less than x using
One of those.
this one.
Yeah.
X is less than y implies y is not less than x. So,
Contradiction.
x is less than y implies y is not less than x, y is less than x. Those two contradict each other. Contradiction.
That's an if and only if. Or now it's a.
No. So we prove that one and only one of these three cases has to be true. So for any two numbers you have, they're either equal or one's greater than the other.
Yep.
Make sense? Okay. Where were we? Oh, now we're on this one. Show that if x is less than 0 and y is less than z,
If that's what?
if x is less than 0,
15, not 16.
yeah, so we need to show, we're going to prove if x is less than 0 and y is less than z, then that implies x times z is less than x times y. So in other words, when you multiply by a negative number, you flip the
Right.
inequality.
I've always wanted to see a proof for this because that kind of confused me when I learned it in algebra
Okay,
for a little while.
So,
This is
let's
the
do it.
same thing as
so,
axiom.
X. huh?
So this is almost the same thing as axiom and log.
Yeah, but what does this one say?
It says 0 is less than x.
Yeah, it says 0 is less than x. We have x is less than 0.
Mm-hmm.
So x is less than 0. That gives us that 0 is less than...
Y.
No.
Z.
No.
Negative x?
Negative x. Good job. So if x is less than 0, then 0 is less than negative x.
Right, of course.
Right? And where do we get that one? Right here.
Oh, turns out it had a purpose.
Does that make sense? How do we get this to this? Okay, so now we have 0 is less than, we have something greater than 0. Well, if we have something greater than 0, and we have an inequality, we can multiply that thing to both sides of the inequality.
This is so stupid.
So, then y less than z, we can turn this into y times negative x is less than z times negative x, right?
Yeah.
And we know we can rewrite this as negative x times y is less than negative x times z, right? That was from, what theorem is that? That's this one. So going from here to here, you good with that? And then finally, we're going to use this theorem, which says, if you want to get rid of the negatives, flip what side they're on.
Right.
So then, that gives us x times z is less than x times y.
Hey,
And we're done.
No, yes. Sorry.
No, I got it right.
that was pretty good.
Okay, last one is if x is not equal to 0 and x times y is equal to x times z, that implies y is equal to z. And you probably already know how to do this. What are we going to do? If we have x times y is equal to x times z, and we know that x isn't 0,
You're going to get rid of the x.
maybe say it this way. I know then that there exists something called u in R such that u times x is equal to what?
0.
1, not 0.
1.
Right, 1. Because that's what
I'd have to multiply by 0.
Basically,
don't
you're just
want
this is the canceling.
Right, it's a cancellation. The same thing as, I'm going to take this equation and divide both sides by x.
Right.
That's what I'm
Oh,
going to do.
this is setting this up for division.
Are we gonna, why don't we define division here?
Because where would
I already
undefined terms?
X times y equal to x times z.
Let me get into definition, that's right.
We can turn this into u times x times y is equal to u times x times z is equal to 1 times y is equal to 1, oops, not is
Equal to
equal,
y equals z.
gives us 1 times y is equal to 1 times z, gives us y is equal to z, and we're done.
Crazy. You know, this should be the opening of an algebra class, like,
It
so mad we didn't.
very much should.
What do we think take a lot
Sure.
more
I got
sense?
lost
How do you go so fast?
Sorry, I wanted to crank through so we can get into exercises. So let's re-go over this one. I know that x is not equal to 0. Okay? So what does that mean if I know that, in this case it's y? If I know that y isn't equal to 0, then I know that I can find some other number z such that their product is any number I want. In this case I was looking for 1. So I know since y isn't equal to 0, I can find a z such that y times z equals 1.
Because it's for all x.
For all x, for any numbers y and x you pick, I can always find a z that makes this true. In this case, I'm picking x to be 1, and I'm using y to be whatever x we have here. So I know that there is some number that I can multiply by x to get 1. That make sense?
That makes sense.
So for example, if you pick 3, I can pick 1/3, so that their product's 1. For any x you pick, I can always find a u such that their product is 1. So now I take x times y equals x times z, and I'm going to multiply both sides by u. Remember, u is that magic number that when you multiply by x gives you 1. So since I multiply both sides of this by u, now I have a ux here, or 1, and a ux here, or 1. So rewrite it like that.
Pretty much just multiply
And
by the
then-
reciprocal of x.
Right, I basically took both sides. So if x was 3, I multiply both sides by 1/3.
That makes sense.
Make sense? Good?
Yeah.
Sorry I went through those so fast, but need to get through. So that's the end of the theorems. We're on to the exercises. You ready, James?
Not even close.
All right, who wants to do the first exercise?
flu.
I mean, I.
Alright, let's see it. I need to sit down.
When is that surgery? Ever?
I guess it's public information now.
Fuck.
So, the kid is having another baby, so I'll have to push it until next year, because that's when she's having the baby anyways. That way we only pay the deductible ones.
I don't know what that means.
I have to pay a deductible on my insurance. So I have to pay so much more money before I start to get insured. So if I get the surgery this year, and then McKay's having the baby next year, we're gonna have to max out the deductible twice. Whereas if I just wait till next year, we only max out the deductible once.
Smart.
So you're gonna wait till
So you
like
can carry yourself for
Suffer.
financial reasons.
Suffer from finance. It's the story of everything, though, I guess.
Endure a little pain. It's no big deal.
You got something
I
right there.
sniffle.
Huh?
Nothing.
So let x be some real number, then negative x is equal to negative x times 1. Sure?
Distributed property with a negative, oh, you can't do that.
Yeah, you can. We just proved it.
Oh, yeah, we did.
Using
Let's see, negative x is equal to, kind of. I would have put one more step in here. Negative x is equal to negative x times 1. Oh, that's what you did there. Never mind. I was thinking about separating it. So yeah, that works. She changes the order, and then she uses a theorem that, this one right here. Yeah,
What do you mean that
that
was
one's
the hardest one that was?
just fine. I was just saying.
Could you explain to me what just happened?
So she starts out with x is some real number.
Yeah.
So now negative x is some real number.
Okay.
Because negative x is that magical number that when you add to x gives you 0. So once I pick an x, my negative x is now picked. So now we have negative x as a number that we can use whenever we want. So she grabs some random real number x. So then she says then negative x, what's that equal to? That's equal to, so she could have split this up like this. She could have gone negative x is equal to negative, if you prefer, x times 1. Well, that's exactly what she did. I don't know another way to write that. If this is the leap you're getting confused on.
I think it is.
Maybe you
How
would have
did she get
preferred her
that?
to think about it this way. Negative x times 1. Negative x is equal to negative x times 1. You good with that?
Yeah.
And then she could have used this to rewrite that as negative x times 1, and then continue with her proof the same way that she does.
Okay, I'll do
Okay.
the next one.
Make sense now?
Yeah.
Any questions? James? You're letting Jacob go before you? Wow.
Sure.
Way to fight.
I don't know if I thought this through right, but we'll give it a gander.
Well, we go left.
It's basically gonna use the remainder, right? And do the same thing we do it backwards.
Just do the same thing, just switch it.
I'm brain dead. Didn't get much sleep last night.
So I'm thinking, I don't know what you guys are thinking, but tell me if this is wrong. Negative x times y is the same
What the
thing.
heck does that
Rude.
say?
Yeah.
That's a good question.
Negative x. Okay. So negative. Okay, that statement's just not true.
Okay, one thing. Two right here, drag me on the bit.
Oh no.
Negative right there.
Oh no.
Oh, yeah. Am I doing this right? Negative x times y equals
X times negative.
okay.
Yeehaw.
Okay.
That
We gotta let X and Y into the numbers first, but.
Yeah, you're being real lazy. Whoa, what are you doing?
okay. One sec. You want? I thought we were doing lazy.
No, I No. You stay on this side of the board. So I'll let x and y be real numbers. Then negative x times y is equal to.
Negative x times negative y.
Jake, why don't you just go negative x times y is the same thing as negative xy, and then flip the y and the x, and then put negative.
That's too easy. Keep doing it with all the negatives. Let's see where this goes.
Hey, Stan.
This one. Sorry, not that one. I had it ganted out in my head.
Probably theorem 7 again. Just get rid of those negatives.
No. I thought I had it. Okay, I think it is this one, maybe. Okay, maybe we'll do it the other way, but.
Maybe.
X times y equals negative y times x equals negative y.
Hey, wait,
Huh?
can I do something really quick? I think I see an easy way to do this.
He just did.
Wait,
I
did
need
you
to
do
do
that
it.
right?
I want to show you another way.
Alright, let's see the new way.
We'll see if it works.
What?
That black marker's dying. I'd pick a different one.
Well, these ones are also equally.
It's literally
Oh,
just,
there.
it's
I think so.
associated property.
But we'll see.
Well, you
You
distribute
could
it,
do it like this.
right?
You could say, oh,
I
Negative
literally-
parenthesis x times y, right?
Right,
So that means you have to distribute it into the y and the x.
negative x
Yeah.
times y
No,
equals.
so it's actually not distributed property. It's
One
literally
times x
roll.
times y, right?
It's roll 8. Do it.
Yep.
Equals
See?
x
See that?
times negative
It's
y.
literally the first times the second. You apply to first. So what you did is break it apart, flip them first,
Right?
apply to the
Skip
first.
the
Yeah, you just need to do
No,
some
I just-
steps.
I
You
just
need
broke
to
it apart,
break
switch
that with
my
that,
names.
then associate it with that.
Yeah,
So you
I
need two
mean-
more steps.
That's just a sort of,
Just have buildings,
you know, I mean, that's just moving things around.
Right,
Do
but
not
it's moving things
understand
around to
Jake's
make it clear
No.
that you're using that
All
type
he
of.
did was
I
bring
have
up
no
the
idea.
negative,
But yeah, it works.
so he brought up the negative,
So-
and then he switched the order,
I guess I can.
so
Yeah.
then you put the negative back on. So look
So he
at
pulls out
theorem
negative
eight.
one.
Look at
times
theorem
x.
8 and look how
I
it
used
is.
that's
8.
what
Y
I used 8, 1, 8.
equals.
So
So
negative
y.
x, y, all he did is flip the order, so it's negative y,
one.
x.
X times
Okay.
y
Negative y times x.
equals x
So let's
times
leave it
negative
at
1 times y
He's
equals
doing,
x times
No,
negative
he's just
Example
trying to
one.
do it a simpler way. He's just trying to one up me.
Just-
Mine was not good enough. We're not kidding.
No, it's just a different way. You just pull out the negative, and the nice way about the way he's thinking about it is it generalizes to any number of terms. You just pull out as -1, and you move it on wherever you want. Okay, who's doing the next one?
I'll do the next one.
All right.
Yeah, Levi's makes way more sense to me.
All right.
Thank you, Levi.
That's the nice thing about it.
Saying he's expired.
Shoot.
Okey-dokey. I haven't looked at it, so I don't know how to do it yet. See,
It's
Jason's
almost
thinking ahead.
exactly how you do it, just algebraically. Same way pre-algebra students do it.
I have teachers in my room. Right, hardcore.
Like hardcore?
Right here. Okay.
The great symbol you got going on.
Y minus z, x
The
minus
great
z.
symbol.
Oh,
The king
Oh,
is
that
a
I
was
bet
so
you I
easy.
could do this one, yeah. Like, little me could do this.
You're just gonna separate it.
Which one do I
You
use?
could have very
Use
the
theorem
very
12.
person does it.
Use
Oh,
theorem
there
12,
you go.
there you go.
Right,
X
so
plus
right.
y equals the same
Okay,
x
just
plus
think
negative
out
y.
there.
Okay.
Like when you
And
have
then
the
you'll have
obligation to
plus
write
y.
on the board, you
Yeah.
bring
And
this
then
out.
Okay.
Maybe.
1.
Yeah.
Now I see.
One. Let x, y, z in the real numbers. Oh, whoops, such that x minus y. Oh, that's somehow, that doesn't make sense. I
Yeah,
remember
you don't
doing
get to
that.
assume it.
I remember doing that a bunch of discrete math. I think I've had it before.
Yeah, you can't say, let me have numbers such that my theorem's true.
Okay, then
The great part is when
y.
they assume the theorem's true, and then they work their way away from it and come all the way back to where they started. I love when they do that.
Equals x times. No, not times. X plus negative y, right?
Yep, x plus negative y plus negative z.
Yep. Negative y
Right, James?
plus
Just
y
x.
plus
Sure.
negative z.
What rule did you just use?
No.
He's using theorem 12. X minus y we can now just replace with x plus negative y.
Which equals
And same with the y minus z.
minus z. Ta-da!
On number
Hey, if you
4,
eat that for about
how would
2
you
minutes,
smooth it?
then I
Like,
might get it.
it's already
You get it really
x
easy
and
this one.
except
Look at this one.
negative.
X minus y
Yeah.
is x plus negative y. X minus y is x plus negative y. Y minus z is y plus negative z.
Y's cancel.
Oh, so he's using theorem 12 twice.
Yeah, he uses it twice. He uses
Three
it once
times,
for this,
actually.
once for this.
Three
No,
times.
just twice.
I used it 3 times.
Oh, when we're all said done. Yeah, but right here we've used it twice, right?
Mm-hmm.
And then y negative y is
Come on, Levi.
0. And then you can get rid of the 0, so you're
Well,
left with
problems.
x plus negative z. Use the theorem again, is x minus z.
Okay.
That was pretty fun.
Make sense?
Yeah.
Got my
Think you can reproduce it?
worked out. You could reproduce it
This
before I
one?
could even.
Yeah.
I think I could, yeah.
Alright, try it out the next one then.
It's the same thing.
Is it?
Exercise 4. We'll find out.
It's pretty much the same thing.
Can I
after
keep
you
this
distribute.
up here?
He'll use
Yeah.
theorem 16, right? No.
How?
No.
Yeah, that's the way it works. You have to remember it in your head.
Oh, now
No.
I
Yeah,
understand
I
how to
think
do this.
We keep this up
That
here.
makes sense. Okay. You just pull it out and get it into a plus.
Okay, wait. I haven't even looked at it. Whoa, your time's in.
You mean it's not the exact same problem?
This looks familiar.
Yeah, how can you rewrite that? So just start by rewriting it.
Rewriting it.
Yeah, distribute it.
Well,
Well, let me,
can't
No.
distribute yet.
let me do
Do
this weird
exactly
number
what
thing.
Levi did.
Alright, do the weird number thing.
Okay.
I.e. let x, y, and z be real numbers.
What is
That's int. This is a
Is it
set of
an
all
arrow?
real numbers. No, it's an
Like
epsilon.
E.
What's an epsilon?
So
It's a curve with a line.
it's like
It's like
that
it's like
with
an
a
E.
line.
That's not
That's
epsilon.
pretty cool.
That's too
That's a lowercase one.
That is not epsilon.
It's a lower.
That is
case.
epsilon.
You're thinking of.
So Peter, do a Levi
Think of
and put it in terms of addition instead of.
In terms of addition.
Yeah, but why minus
I can't
z
tell you
in
what
terms of
epsilon is
addition?
in my head, but there's no way that one's epsilon.
So do this.
That's what it's called.
In terms of addition.
So I just have the x at the first cell, right?
Yeah, so x times, it's still in parentheses.
This big thing, right?
No, that's mine.
No, you need to look at yours.
I know, I'm just different.
So start with this.
Rewrite your.
Just write this exactly.
Oh.
X times y minus z. Now, how can we rewrite this?
Put the
Well,
line
you can
to uses.
rewrite it just as he's doing, except y plus negative z, right?
Well, that's how you can rewrite the inside,
Yes.
but you still need your x.
Oh. Yeah. theorem
Keep your
12.
parentheses as well.
Okay,
Put your parentheses on there so we know how that's
Well,
distributed.
yeah, so you have x times
The whole term.
y plus negative z,
oh, yeah.
right?
Mhm.
And now you can distribute.
Distribute.
X times Y.
Using your action.
Right here, number 3. X times y plus z is just equal to x times y plus x times z.
Do I still need my parentheses?
There you go.
Z.
Much different. Much
That's
different.
also an epsilon.
There's a uppercase
That's
and
also
lowercase.
uppercase.
Never would use that in my whole.
It's kind of like a cursive version of it for the Greek.
Isn't it? I thought they had
I'm
uppercase and
going
lowercase.
to get it.
I always did epsilon that way. Did I? I never did epsilon that way.
Whoa.
We reserve this one for talking about sets. We use this one for when we're talking about a small number.
Okay,
You
now bring
think
your
of
negative
delta?
out.
Yeah, how do you bring your negative out?
Look, theorem 12. Or not 12, but,
7.
Well, exercise
Yeah.
one.
Seven.
not 7, 8.
8.
Yeah, 8.
12, 7, 8.
Oh, yes.
So you're
So
So
X times
negative-
Y minus
minus
X
X
times
times
Z.
Z.
Now please fix your Z's, dude.
X times Z.
It's on the Z.
Shouldn't this be in parentheses?
Just how line through it.
Yeah.
I've been reading Y minus 2.
Right?
Y minus
Yeah.
2.
Shouldn't my X be in parentheses?
Well, you just.
You want parentheses where?
You
No.
don't need to.
I don't
Just
need to.
print it.
Oh,
If you like them, you can put them there.
I like them.
Alright,
It
so
doesn't
stick
make
them
sense without them.
Now you gotta.
That makes more sense to me.
No! You
there. Then
can't.
it has to be a plus. No. Yeah, no.
Oh, I
thought
can't do
you were
that.
doing it different. Yeah, no, you can't do that, otherwise make your product. So you
where
need
did
to
these
use.
parentheses go then? They just
So-
disappear?
Parentheses can come and go.
So look at this. Oh, so this is still just x times y, so you're good with this. So we have x times y still, and then you had a plus negative x times
Negative.
z. No? So
Yeah.
that was using
So I skipped a step. It was,
this, right?
yeah.
So you pulled the negative out, and now you have this plus a negative number, which is exactly what we mean by minus. So that's x times y minus x times z.
That's where the parentheses went. That makes sense.
Good? All right.
Neat.
Leah has the W variable.
5. I'm trying to figure out in my head, but I can't.
5?
Yeah.
Just do what you want to do and you'll get there. Don't bother with all this other stuff. Just start with this and show it's equal to this. Don't do all the other stuff. on the
Just
side.
saying algebraically.
Yeah, how you would algebraically do it is you're
Just
just
like
gonna
the
do it.
right curve to it.
Why is
You're
my
just gonna
curve
accept
still up
it.
there?
Okay,
Huh?
so
This
X
is why my
squared
curve is still up there. It's not even that cool.
Plus y plus z minus w. Okay, so what are those?
Okay, so I think you need to change it into, let's just get rid of this, so it would be x plus a negative y plus z plus a negative w.
Okay. So
Now,
you know,
I can switch this.
Yep,
Yeah, there you go.
you got it.
Yeah, now we're in like first grade math, dude.
Hey,
This
cool.
is actually
Just like a fourth
Then
grade.
you have negative y
Fourth grade.
and then plus a negative
Fifth grade.
w.
Oh, there's variables, so it's more like that.
Right there, dude. You have it.
Yeah, you have it.
Pretty close. How should you
I think that's
justify
right.
factoring
How do
out
you
your
justify
negative?
factoring out your negative? That's a good question.
Yeah.
We can only factor out numbers. How do we go from negative y to a number in
You
y?
just use exercise one?
What?
Throw ones on those.
Exercise one is so
Just
convenient.
go negative one
You
on
can
them.
just like use it, simplifies things.
Now we can factor a number out by the reverse distributed problem.
now you just factor out the -1, and then use exercise 1 again.
Oh, by distributed property?
Uh-huh.
Oh, I see.
No, reverse.
Ignore what he's saying.
Yeah.
Which way is using the associative property and which way is using reverse associative property?
Wait, it goes from left to right, not right to left.
There we go.
X plus x equals 0 implies x equals 0.
But I mean, it's not really like a proof, but.
Alright, x plus x equals 0 implies x equals 0.
Why is there 2? Oh.
The other one's times.
But we have
James and Emma.
a process of elimination.
I can be eliminated, that's fine.
Alright, let's do these ones real quick. Let's think. I just want to do a proof by contradiction.
Assume
How you
x is
can
not
just figure
0.
that out by looking at it blows me away.
Well,
Proof by contradiction, shall we?
only maybe. Let's see. So x plus x is equal to 0. We have that. Assume by way of contradiction
X is not 0.
that x is not equal to 0.
Then I'm guessing you get your inequality.
That's kind of weird.
Well,
Yeah,
yeah,
we
how
don't
do you
like
prove that
that.
x is not 0?
Oh, here's an easier way to think about it. So x plus x is 0. Since x is a magic number that when I add to x I get 0.
Right.
So that gives me that x is equal to negative x.
Which is a contradiction.
Not a contradiction. So then
Oh,
x
that's right.
plus x is equal to. Oh, where was I going with that?
Where
Wait,
are you?
what?
-0.
How'd you get x
zero.
equals negative x?
Because x plus x equals 0.
X
Oh,
plus
and
x
then-
equals 0, so x equals negative x. I thought I saw something in my head, but I didn't have what I thought. So let's see. I want to show that x is equal to 0. I know that x is equal to. And I know x plus x is 0, which gives me x is equal to negative x.
Can't you just say, oh,
Don't have what I thought. Anyone have any ideas?
I keep
Theorem
looking at
number
8,
one.
5, or
Wait a minute.
you don't have a 0 used.
Yeah, actually. You could use
I
exercise 1 and take the -1 out and then eliminate x from both sides. -1 times something equals 0. So that something has to be 0 and that's x.
Well, now you're using word roundabout logic.
So it works.
Well, not really. The things you're relying on to prove it is more questionable than just saying obviously it has to be 0.
Okay. You're probably right.
No, there should be a simple way to write x equals 0 somehow out of this.
Plus 0 equals 6.
So I know that x is equal to x plus 0. Yes, I know that is equal to x plus negative x. Yeah, I can say that. I know that my x plus x is 0, but that just gives me x equal to negative x again.
Feels like there should be it should be obvious.
There should be something very straightforward to
This should
this.
be very obvious.
X plus negative x. Okay, 0 equals negative 0, so x plus negative x equals 0. I don't know.
We know that 0 equals negative 0. We don't know that anytime x equals negative x, since x has to be 0.
But you know that for all other numbers that isn't the case. 3 is equal to -3, 1 is equal to -1.
How might you prove that for every other number? Just do it. Right, that doesn't work.
Do it by induction or something.
Let's try the contrapositive, maybe that will help, just an idea. If x is not equal to 0, can we use that to show that x plus x is not equal to 0? That's kind of weird, isn't it?
how would you prove
That's a
that?
lot harder, don't you think?
Yeah. Just thinking out loud.
I think your by way of contradiction is probably.
Isn't that basically by way of contradiction?
Probably has
Then
a
you'd be proving
more
x is
promising.
not 0.
So let x plus x equals 0.
Assume by way of contradiction, x is not 0.
And by way of contradiction,
Try it,
that x is
Yeah.
not equal to 0.
because then something plus something equals 0, and the other.
See, this would help us with this one, but not with the first one. Should we do 7 real quick while it's on my mind?
Why not?
Yeah.
So let's really quick make this x times x equals 0. So x times x is equal to 0. I'm trying to show that x is equal to 0. If I assume by way of contradiction that x is not equal to 0, then there exists y such that x times y is equal to 1, right?
Yeah.
Okay.
So then, x times x equal to 0 can be rewritten as x times y equal to 0 times y, which is x times 1 is equal to 0, which is x is equal to 0.
Which is contradiction.
Which is contradiction, and so we're done. So that's 7. So now we just need to figure out how to do 6. Everyone give a 7?
Kind of.
Kind of. Let's go over it. I'm trying to show that x times x equaling to 0 implies x is equal to 0.
Mm-hmm.
So I assume by way of contradiction that x isn't 0. I'm going to show that leads to something impossible, therefore x is 0. So assume that x is not equal to 0. Since x is not equal to 0, then there's some number I can multiply x by to get 1. Call that thing y.
Okay.
So y is now that special number that when I multiply by x I get 1. So now take this equation and multiply both sides by y. With me?
Yeah.
What's 0 times y?
0.
0. What's x times y?
1.
1. What's x times 1?
X.
X. X equals 0. Assume by way of contradiction that x is not equal to 0, x equals 0. Contradiction. Therefore our assumption is false. Therefore x does equal 0.
Donnie, with 6, could you go x plus y equals 0, then if x equals y, then you could just
Yeah,
replace y
use the
with-
same logic.
So, 1 second. So I have x
Assuming
plus
by way of
y
contradiction,
is
then.
equal to 0. What were you saying?
And then with your logical, or that x is equal to y, and then
True. Assume by way of contradiction that y is not 0 here.
Continue with your line of thought that you were saying. X plus y equals 0, then what?
then if x is equal to y, you just replace it with x, and then x plus x equals 0.
You're doing something weird there.
Saying let x equal y.
But Jake, what were you saying? By way of contradiction?
So we
Proving
start
that
out
y
with
is not 0, but that would
x
be saying
plus
that
x
is not 0.
0.
is equal to 0.
And we know from a rule,
It seems like we should easily be able to get x equals 0 out of this.
Seems like it.
We're missing something so obvious it's stupid. Let's start here. X is equal to x plus 0 is equal to x plus minus x is equal to, hey, there we go. X plus minus x is equal to 0. Okay. Easy peasy. Can't really fix that one. X is equal to x plus 0.
How'd you get that?
That's just in general.
Yeah.
Anything plus 0 is just that thing.
that's
Oh.
A4.
Yeah.
Okay. 0 can be rewritten as x plus negative x.
Mm-hmm.
So, what's x plus x?
0.
Oh, 0. I replaced it with an x. I cheated.
Oh.
Yeah, that doesn't work. I cheated. Because, yeah, we had x plus x equals x. We're done.
But it does.
Come on, man.
Ah, sugar, sugar, sugar. Yeah, because all we get is 0 plus negative x once again gives us x is equal to negative x.
That's gotta be the keys for, like, somehow.
Well, it's logically equivalent, but.
Maybe if we use, huh. Hey,
I
no.
still think we're using theorem 5 on this.
Theorem 5?
There only exists one y to make x plus.
Right, negative x. So I know x equals negative x.
Yeah.
Negative x is the one and only one that we can do. Alright, so let's go proof by contradiction, bring inequalities into this even though I kind of want. X plus x equals 0. Assume, by way of contradiction, that x is not equal to 0. Then we have two cases.
X is greater or x
And
is less.
x is greater than 0 or x is less than 0. Right?
If x is greater than 0, then
Actually, this isn't a symbol. We have either x is less than 0 or 0 is less than x.
look, if x is greater than 0, it's a positive number. If
So,
x is less than 0, it's a
one.
negative number. Therefore,
If x is less than 0,
it has to be a negative number.
that gives us x plus x
That gives us x plus x is less than 0.
is less than 0 plus x.
Why didn't we just do that to begin with?
Aren't you
That's
trying to
not
get x equal
helping.
0?
X is less than 0.
But you assume that x is equal to 0, and you show that if x doesn't equal 0,
I
it has to
understand
be
that.
less than 0 or
Yeah.
greater than 0. You show both of those are false, so that x doesn't.
Then we get x plus
Oh.
x. Oh, there we go.
It's a common.
So add x to both sides, we get x plus x is less than x,
So,
Plus.
which then gives us
Because it
0 is less than
works so
x.
well.
Contradiction because
Not
x
destroying the
is less than 0. I can't have x
How'd
less
you
than
get
0 because 0
0?
is less
There you
than
go.
x.
How'd
Yeah,
you get
that's
0?
fine.
X plus x is 0.
Okay, there you go.
No, it's not. Oh,
Right?
wait a minute.
So I didn't
Oh,
want to
you're
do it
doing
this way,
by
but
contradiction.
shouldn't have been
Lazy.
so hesitant. Yeah, lazy. Next, if 0 is less than x, then we get that x is less than x plus x, which gives us that x is less than 0. Contradiction. So proof by contradiction did work. I just didn't want to use inequalities when I should have.
Which
Alright.
means x
Not
is
that bad.
So is there any homework on this section?
Yeah, there's tons of homework. We went through all of chapter 7. We didn't just do a section.
this was all of chapter 7.
Yeah, so that's all of chapter 7. I strongly recommend re-going through the theorems, making sure you understand them.